Okay, we're going to look at some examples of drawing constitutional isomers. So if I give you a formula, contains 3 carbons, 8 hydrogens, and 1 oxygen, and I tell you to draw 3 different constitutional isomers for it. Okay, draw 3 different ones. Well, I'm going to give you some tips to kind of help you out here. When you have oxygen present, you always say that you can have an alcohol. So I would start and draw my straight chain of carbons, a 3-carbon chain, and then I would put an alcohol group, a hydroxyl group on the end. So if we count a number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogens, 3 carbons, 1 oxygen. Okay, another thing that we can do is still keep our 3-carbon chain, but then branch the hydroxyl group off of the second carbon. So now we have two different structures, because remember, constitutional isomers have the same chemical formula. They are just different in that their atoms are connected a little bit differently. Okay, atoms are connected differently. Remember, that can include double and triple bonds. So we basically have gone through our possibilities for having a straight chain compound of carbons, because we have a 3-carbon chain. If you were to move the hydroxyl group on the second compound over to the left, it would be the same as the first compound. So remember, you can always go through and double check with naming, see if they're the same. The other type of structure you can have when you have an oxygen present is an ether. So this is one possible ether structure. Okay, and now we've come up with 3 different constitutional isomers that fit this formula. Okay, you can go ahead and pause the video if you need to, because I'm about to clear the screen, and we're going to look at a different structure. Okay, the next formula that we're going to look at contains 4 carbons, 10 hydrogens, and 1 oxygen. I'm going to tell you that you can make 7 different constitutional isomers. So following our hints, I would start out with straight chains, drawing straight chain structures and putting hydroxyl group on different carbons. So if you want to, go ahead and pause the video and see if you can come up with 7 different structures. Okay, the first one would be a 4-carbon chain with a hydroxyl group on the end. I'm going to rewrite that so it's a little bit clearer. Four-carbon chain with hydroxyl group on the end. Okay, the next structure we could draw, well, we could branch the hydroxyl group from the second carbon. Now we've used up our 4-carbon chain possibilities. Now let's go down 1 carbon to a 3-carbon chain. One thing you could do is branch your hydroxyl group off of the carbon chain along with the methyl group. So for example, this would be 1, 2, 3. For numbering, actually for nomenclature, the hydroxyl group would get priority. So I have the number 3, that should be number 1. But at least you can see the 3-carbon chain there with those numbers put in. Okay. The other structure could look like this, where you have everything coming off of one central carbon. Okay. Those are your only possible alcohol structures. Now let's look at another possibility, which would be ethers. Okay. One possible ether structure could be this compound. 1 carbon here, your second carbon, 3rd carbon, 4th carbon. Okay, count your number of hydrogens, that equals up to 10. Another structure we have a 3-carbon chain attached to the oxygen, and then you have a methyl group that's coming off of it. That's another possible ether structure. And then finally, your last one, the oxygen. It's almost similar to isopropyl alcohol, but your oxygen is actually coming off of one of the carbons in the 3-carbon chain, and then you have another methyl group that's attached to it. So hopefully this gives you a little more practice with constitutional isomers. Other thing I want to look at in this video are just some example resonance structures. So if I give you this formula, this compound, and ask you to draw the best resonance structures for it. Well, one possible resonance structure we can draw, remember, when you draw resonance structures, to include the appropriate arrow, is to move these electrons in, so they're now forming a bond between those 2 carbons. So when I redraw my structure, you have your double bond there. Now my positive charge would be on this carbon, and this double bond would stay the same. Okay? We can draw one more. We can draw one more resonance structure for this compound. Okay? I can move those electrons there. Remember, when you're drawing your arrows, you start where the electrons are, and then you draw the arrowhead indicating where they are going. So a double bond between those 2 carbons. And then you have a positive charge on this carbon. Okay? Those are the best best resonance structures that we can draw. Cannot move the double bonds anymore, because remember, the rules for resonance structures, one is you need to make sure you try to have as many atoms as possible with a complete octet, and then you don't want to also continue to build up charge. Okay, you want to minimize positive negative charge as much as you can. And if you start moving, say if you moved this double bond here, that violates those rules that we just talked about. Now you're creating another positive charge. You would create another positive charge on this carbon. So that would not be good. Okay? So the 3 original structures that we have, those are the best resonance structures that we can draw for that compound. Right? I want to look at one more example. So make sure that you're reviewing your rules for resonance structures. They're listed in the chapter. But if I have this compound and ask you to draw a resonance structure for it. At first glance, you may think, well, I can move the electrons in the double bond. But what that does is it creates several problems. It leaves this carbon without a complete octet, and then also it creates more charge on bromine. Okay? So remember, with bromine, we have your lone pairs of electrons there. So if we were to move these electrons over here, there would now be a double bond to bromine, which isn't good. That's not the best thing that we could do. You have a buildup of negative charge there. And also you would have a buildup of positive charge that would be left for moving the electrons from orbitals between those 2 carbons. So buildup of charge is no good. Also, it would leave this carbon that we already mentioned before with the arrow pointing to it without a complete octet. So the best thing that we can do for this structure, the best resonance structure that we can draw, would consist of moving in a pair of lone pairs from bromine and form a double bond, and then move a pair of electrons onto that carbon atom. Okay. Now we have a positive charge on bromine and negative charge on carbon. While yes, that's not 100% the best case scenario, this is still the better resonance structure, because number one, we're not taking away electrons for a complete octet. So it's okay. It's okay to have that negative and positive charge. We could not draw a resonance structure with what we mentioned before, with moving electrons in from the double bond.